From averages to insights, exposing the flaws in DMS plant design. When we look at a dense medium plant, whether it be commissioning or operation, we are faced with a number of challenges. And some examples of these challenges are feed prep screens. So visually, if you look at that screen, everything looks fine. If we stop the screen and we inspect the panels, we find that there's a lot of pegging. Now, these panels are slot with flow panels. And even in spite of that, we have a lot of pegging. Pegging leads to reduced open area. We get increased undersize and oversize. It leads to medium contamination, and we get increased non-mags and viscosity in our medium. If we look at drain and rinse screens, this is an example of an iron ore application, 8 by 1 millimeter. You can see on the sink screen, it's not draining at all. In fact, the medium and the ore are running over into the floats section. Another example of a split drain and rinse screen. So on the left-hand side, we've got the sinks. On the right-hand side, we've got the floats. And above the yellow line, we've got the rinse section. And you can see on the sink side, we're just not draining the medium at all. Whereas on the float side, the medium is draining. And again, this leads to carryover of medium and various other issues. So drain and rinse screens specifically, what happens when they don't work? You drop the level in the correct medium tank. You overload your magnetic separators. And in the process, you increase your medium consumption from hundreds of grams to kilograms. If we look at screen loading, this is a sink screen. You can see it's very underloaded, very low yield. If we look at the bottom picture there, we find there's a typical loading, and that is due to sink's yield variation. So when your sink's yield increases, you increase your medium carryover to the dilute circuit. You increase the loading on the magnetic separator, and you increase your medium consumption again. If we look at magnetic separators, there's a typical countercurrent magnetic separator, which is used in a dense medium circuit. On the left-hand side, we've got an underloaded mag sep. There's a trickle coming out of the feed pipes into the feed of the magnetic separator. On the right-hand side, that whole feed box is overflowing because there's just too much dilute medium being pumped to the magnetic separator, and it can't handle it all. What is the result? The result is magnetic recovery gets affected. And on the right-hand side there, we've got the effect of recovery or efficiency versus feed concentration. And as you go from underloaded to overloaded, you're changing your feed concentration and your recovery. And again, it leads to increased medium consumption. The overall effect is that you can end up with a plant that looks like that, where you're virtually all your medium inventory is sitting on the floor. You can't run it. You can't do maintenance. It's just a mess. So what is causing this problem? Is it the flow sheet? If we look at the flow sheet and we go back to the patents issued by Stanley Carbon from Dutch Mines in the Netherlands, this patent was issued in 1949. If we look at it, it has a correct medium tank / mixing box. It has a dense medium cyclone. It has drain and rinse screens. There's a dilute medium tank. There's magnetic recovery. And it has density control. We come to the 2000, we find that what has changed? Yes, we have densifiers now, which they didn't have back then, and we've improved magnetic separators, but all the fundamental building blocks of the flow sheet are the same. So it's not the flow sheet that's a problem. Is it the equipment design? And in equipment design, we talk about screens, cyclones, pumps, densifiers, mag seps, etc. Most of the equipment that we use in our dense medium plants is proven. And generally, it's as good as the design information provided. But sometimes errors are made and equipment doesn't work as specified. Is it the design inputs? Inputs are derived from test work. So the questions to ask there and that affect what's happening is how representative are the test samples of the ore body? And also how much variability test work has been conducted. And in many cases, plant designs are based upon limited test work. Is it the mass balance? What we're trying to achieve with the mass balance, we're trying to get all our streams, but then we also want the ore tons in to be the ore tons out, the water in, the water out, the medium tons in, the medium tons out. And you can see below there, all the ins and outs and the deltas are zero, so everything balances, and the mass balance balances. So To say the mass balance is not the issue because it does balance. Is it the mass balance inputs? The inputs normally consist of the following: an average value plus a safety factor plus maximum values per stream where applicable. The problem is that we are dealing with perceptions. And depending upon the angle and our viewpoint, we see different things. The underlying assumption is that the plant runs under steady state conditions. Everything is balanced, everything works as it should, and there's no disturbances. Reality is, however, very different because variability is the norm. And examples are changes in the ore properties as it is mined. Your PSD can change, your yield can change. The equipment performance degradation, as equipment wears, its performance changes. Process control, which does not control as it should, so loops that are not properly controlled. And then variable speed drives, which are great when you're commissioning a plant, but give the operators the opportunity to fiddle around and upset a plant. Look at an example of particle shape. Our perception is often nice round particles, maybe cubical particles, but when your reality is elongated particles as shown there on the right, it has a major impact on your plant and the operation and the design. If we look at particle size distributions, for example, we often design on a single curve, and we assume the splits, if we've got a split DMS design, to be constant. But the reality is that the particle size distribution is changing all the time as blasting changes, as crushing changes, as the ore properties change. And we end up with an envelope of particle size distribution which our plant sees. So the major cause of the problems we experience is variability. If variability is the major cause, how do we capture variability? And we do it using probability. So if we look at probability distributions, most of you are very familiar with the normal or the bell-shaped or the Gaussian distribution. If we look at the graphic on the left-hand side, it's a curve, you see it's a nice bell-shaped. So what do we need to characterize it, to quantify it? You need a minimum of 30 samples. You calculate the average, you calculate the standard deviation, and then you can draw certain conclusions. So we can say plus or minus 1 standard deviation of the mean, 68% of your values will fall in that range. If we take plus or minus 2 standard deviations, that'll account for 95% of the values, and 3 standard deviations will account for 99.73%. And Excel, and we use Excel, everything that we do nowadays, Excel is our default, our go-to method of doing calculations, mass balances, etc. We've got some nice functions here for the normal distribution built in. You've got the norm dist to generate a normal distribution and the norm inverse to calculate the probability given a normal distribution. Another probability distribution is the triangular distribution. And for the triangular distribution, we need to specify 3 values. We need to define the minimum, the most likely, and the maximum. And if you look on that triangle, and it's called the triangular distribution because you generate a triangle, it doesn't have to be symmetric. So the values that you choose, they can be based on test work, they can be based on experience, or a combination of both. And this is a recommended method for capturing variability. For example, in a plant, you've done some test work, you know your yield that you saw there varied between 20 and 25%, but you've got experienced people around and they know in similar plants it can actually vary from 10 to 40. So then you'd say, let's make 10 the minimum, 40 the maximum, the most likely 20. So it gives you a lot of freedom, it's a lot simple, and it allows you to blend in experience, whereas if you take the normal distribution, you actually need just values. How do we use it? Application in Excel, again, we use Excel, we define it. So we've got the minimum, we've got the mode, which is the most likely value, and don't confuse the mode with the average. And then we've got the maximum value. What we then do is we generate a random number between 0 and 1, and we calculate the corresponding value from the distribution. We can use the lambda function in Excel. So if we look at that on the first line, we've got lambda, and the lambda is a relatively new function in Excel. It enables you to move away from using user-defined functions and VBA code. The first 3 numbers, the first 3 values, R and N is your random number. Then you've got your min, your mode, and your max. So those are the inputs. And then you say if the random value is sitting to one side of the triangle, you've got a certain calculation. If the random number sits on the other side, you've got a different calculation. We use a medium split example. The medium split to the underflow of a dense medium cyclone. And on the left-hand side, you've got a photograph. You can see the medium coming over the spigot. So it can vary between 10 and 40% of the feed if we look at the date mines values. And the most likely value is 20%. So in this case, we define the minimum as 10, the mode is 20, and the maximum is 40. There's a probability density function that we now created. So on the x-axis, your minimum is 10. The highest point of the triangle is at 20, because that's the mode, the most likely, and the maximum value is down at 40. Then to do the simulations, we convert this into a cumulative distribution function. We generate a random number. So on the x-axis there between 0 and 1, we've got a random number. And as we generate the random number on the curve, we read off what the value is. So you can see there, the first gray line there is at 10, which is the minimum. Then you've got 20, which is the most likely, and 40, which is the maximum. And as you generate these random numbers, you can see you pick different points of that curve and you generate different values of the medium split. We need to talk about dependent and independent events. So if you look at the minus 10 millimeter on a PSD, and to apply the triangular distribution, we have to define the minimum, the mode, and the maximum value for the 10 millimeter. If we look at the minus 1, again, to apply the triangular distribution, we have to define the minimum, the mode, and the maximum for the 1 millimeter. But the percentage minus 10 and the minus 1 are dependent. So as size distributions get coarser or finer, the minus 1 and the minus 10 will move up or down in synchronization with each other. So when we simulate dependent events with a triangular distribution or with Monte Carlo, we use the same random number to generate the numbers for both distributions. We don't use different random numbers. If we now look at independent events, if we now go and add the medium split, the medium split is independent of the PSD because medium split is governed by the cyclone, the operating values, the yield, and so on. So we would then generate the size distribution minus 10 and minus 1 with one random number, and we generate the medium split with a different random number. And that's how we handle dependent and independent events. If we look at a Monte Carlo example, here's a simplified flow sheet. We have a feed preparation screen. We've got our screen feed coming in on stream 1. The screen oversize goes and feeds into a mixing box. Stream 2, we add medium, which is stream 7. We pump it to a cyclone, which is stream 4. And the dense medium cyclone splits it into a float stream and a sink stream. And those floats and sink streams will go to their relevant float drain and rinse screens. What are the variables? The variable streams are the screen oversize, the cyclone yield, and the cyclone medium split to sinks. What are the fixed streams? Is the screen feed and the DMC feed medium. And what are the dependent events of the cyclone yield and medium split? So what we're saying here is as you increase your yield, your medium split will increase because the more that ore you've got to get out of the sinks, the more medium it will take with it. Here are inputs and just the convention there. So you can see an input block is defined by a black text on a orange background, whereas a calculation is a orange text on a gray background. So if we look at it, for our inputs, first thing is our screen feed. The value we've got here is 350. It's not a Monte Carlo variable, so it's fixed. The next one is the screen oversize, and we can see that's a calculated value. It's a Monte Carlo variable. The minimum is 40, mode 45, and maximum 60. And for a normal random number between 0 and 1 which you can generate, and the value is 0.055, the corresponding value for the screen oversize is 42%. The medium addition is 400 cubes an hour. It's not a Monte Carlo variable. The medium split to sinks is a Monte Carlo variable. You can see it's a calculation. Minimum 10, mode is 20, maximum 40. And then for a random number of 0.079, the medium split is 29. And then the yield to sinks is another Monte Carlo variable. And so we find the minimum there is 30, 45 for the mode, and 60. And in this case, because they are dependent, we use the same random number for both. And then for 0.792, the yield to sinks is 50. So now we can go and we can calculate our mass balance. We've got our screen feed, oversize, undersize. We've got our DMC feed tons and volume, our DMC sinks, tons and volume, floats, tons and volume, and our medium addition. And so we've generated our mass balance. What we then do is we add a bit of Monte Carlo code. And that's just really that we solve the mass balance and then we copy the results into a sheet and we do the next solution. And that's what that Monte Carlo does. It looks quite complex, but it's actually very simple. So at the end of it, what is the result of this? We normally run, for Monte Carlo, we run 1,000 simulations. So what are we generating is we're generating 1,000 different alternatives or scenarios of our mass balance. And in each one, we're getting the combined effect of all of these changes in terms of screen oversize and yield and medium split. And so streams 1 to 7 correspond to our mass balance or our flow sheet numbers. And then we've added 5A and 6A. Those are the medium, the DMC sinks medium and the floats medium. And we've got our runs, so it's our simulations from 1 to 1,000. And at the bottom, I've calculated the illustration, the minimum, the average, and the maximum. So you can see the screen feed was fixed, so it's all the same. The medium addition, stream 7 was fixed, they're all the same. But all the other numbers, the minimum, the average, and the maximum vary. And that's because they've been varying from the Monte Carlo. Now, if we just use the average value here, we're back to where we started. And we haven't really done anything at the end of the day because these will be similar to the mode values that we put in. So after 1,000 mass balances, we go and we analyze the results. On the top here, we plot it as a histogram. And on the x-axis, this is screen oversize. It's in feet tons and the percentage. So that's the distribution of tonnages. You can see that it's got a slightly skewed to the left. And then below it, we've got the cumulative. So we can see that the screen oversize varies from about 140 ton per hour up to 210, which is quite a wide range. The D50 is around about 160 tons an hour. And in this case, we wouldn't want to design an average because remember, we don't want our equipment to be overloaded. We want our plant to be able to handle this variation. So in this case, we pick the 80% point, which will give us a value of about 170. And this is a subjective process, but you can see the slope there is really flat. We don't want to design up at 200 because that will be a very big screen. Because how does this affect? We look at the screen oversize, it's your bed depth on the screen, and the bed depth affects classification. So the more tons, the wider your screen's got to be. If we look at the sinks tons, there's the distribution. We can see it's fairly symmetrical. The sinks tons goes from about 45 up to 120, so it's a very wide range. And the other interesting is to see here at the upper end, it actually slopes up very quickly. So the average value here is just under 80. And because those videos that we showed the effect of overloading sync screens. And it's one of the big problems on dense medium plants is that your sync screens get overloaded. Yeah, we'll be more conservative and we'll choose the 90% value. And the 90% value you can see is over there. It corresponds to about 90 tons an hour. If we look at the sinks medium, you can see the volume goes from 40 up to 160. So again, a very wide range. And again, we've got to drain that medium on the drain screen, on the drain and rinse screen. So here we want to be conservative because we don't want to run out of area to drain the medium. Here we choose the 90% value and we see it's up there just below 140. So in summary, screen oversize, average value is 169. What we selected from the Monte Carlo is 181, so it's 7% higher. The DMC sinks tonnage, the average value is 76. We selected 92. That's 21% higher. And the medium volume, the average was 94, but we selected 129, which is 37% more. So you can see here the difference from if you just use the average values compared to the values from the Monte Carlo with a bit of judgment and a bit of assessment. So that can help avoid, this process can help avoid drain and rinse screen issues. And it applies to your complete mass balance. So on the left-hand side, we've got an average value. So there, this is now the medium split. If we use average values, we've got a single line probability of 1, it's 20 all the time. On the right-hand side, we've got a distribution. We're saying, yes, the most likely value is 20, but it can vary from 10 to 40. And by using this approach, what is the result? It exposes the current design methodologies. These flaws are created by how we handle variability. And most times we're uncomfortable with variability because it's probability and simulations and all these things we're looking incredibly difficult, but which are not difficult to handle in Excel. We incorporate variability into the design process, provides insights with regard to the equipment loading, sizing, and selection. and it results in a more robust plant design and operation. And what we've got there is a drain and rinse screen which is draining. We're not overloading it. We don't have an excessive bed depth. We don't have a lot of medium carryover. We're draining all the medium on the drain section, and then the adhering medium is washed off in the sink section, like in the rinse section. Thank you.